We have already discussed frequency modulation and phase modulation in detail in our last lecture. So now we are discussing the limiting case of the frequency modulation, which is known as a narrowband frequency modulation. So narrowband frequency modulation. We have FM signal. So narrowband FM is used to improve the spectrum efficiency, and it is also used in voice communication and radio setting. So we have FM signal which is equals to AC cos omega CT plus K of F and the integral of the message signal. So if we want to write that signal in term of phasor form, so we can write AC e raised to the power, so this one is the phase omega CT plus KF integral of the message signal. Or you can write this like you can divide that into two parts. So one part is this one and the other part is that one. So that is why you can write AC is equals to e raised to power j omega ct and e raised to power j kf and the integral of the message signal. We know the exponential series e of x is equals to 1 plus x square by 2 factorial plus x 3 by 3 factorial x 4 by 4 factorial and so on. Give the name of and then if this is the case, so we can just use that formula in this equation. So A is C e raised to power j omega ct and then replace this with that formula 1 plus j kf integral of mt dt and then so on. So you can see that the infinite number of side bands. And the limiting case of FM is the narrowband FM. So where beta is much less than 1, or you can say k of f and the integral of the message signal is much less than 1. So you can use this assumption in this equation. So in equation A, and then if you use this assumption in this equation, so it means that if beta is much less than 1, then the higher order terms are again like ignoring, neglecting. The higher order terms are keep small, like very smaller. So you can ignore the higher order terms in this equation, and then the remaining equation is this one. AC e raised to power j omega ct plus 1 plus j k of f and the integral of the message signal. And we know these formulas like e raised to power j omega ct is equals to cos omega ct plus j sin omega ct. We can use this formula here. So cos omega ct j sin omega ct 1 plus j kf integral of the message signal. So if you open this product, like if you open the brackets, then you will end up with this equation AC cos omega ct multiplied by 1. The answer is AC cos omega ct. Like here you multiply this with that one and then you multiply this with that one. Okay, you can multiply turn by turn. So j k AC k of f integral of the message and cos omega ct. So similarly you multiply this with the 1, so j AC sin omega ct plus j multiplied by j its square AC kf integral of message sin omega ct. We know that the square of j square is equals to minus 1. So you can write this term here. So AC cos omega ct AC kf integral of message sin omega ct, and then this j and this j you can take common, jac. So kf integral of the message signal multiplied by cos omega ct plus sin omega ct. You can take the real part from this equation only. So the real part is this one, only you have real part is that one. So this one is real and this is imaginary. So you can take out the real part. So real part is that one. So real part AC cos omega ct plus AC kf integral of the message signal multiplied by the sin omega ct. So that is the limiting case of the single tone modulation. Like in single tone modulation, you suppose that your message signal is equals to AM cos omega mt. So if you replace this mt with that assumptions, so you can write AC cos omega ct minus AC k of f AM cos omega mt dt minus multiplied by sin omega ct. And we know, so AM is constant, so that is why AM is outside, and the integral of cos omega mt sin omega mt divided by omega m, and you know this part is known as the modulation index, which is beta. So you can write AC beta by 2. So also we know this trigonometric formula 2 sin A sine B is equals to cos A minus B minus cos A plus B. So you can use this same formula here. So sine A, so this one is sine B and this one is B, this one is A. So sine A and B, so you can divide and multiply it by 2. So that is why you are writing here AC beta by 2. So cos omega C minus omega M. So this one is lower sideband and this one is upper sideband. So if you want to write in term of spectrum, so that is the central frequency omega C and these are the positive side. So like pi by 2 AC beta and this one is the negative side pi AC by 2 beta. Or you can write the same thing if you are considering mt is equals to a sin omega mt, like this is your signal AC cos omega ct plus beta sin omega mt. So if this is your PM signal, so you can take the integral of that one. It's like you have already taken the integral of the message signal, like here, like your message signal was something like that, k of f and the integral of am cos omega mt and dt. So k of f am by omega, so that is your beta, so that's why you write beta, and the integral of cos omega m is sin omega mt. So you can write this one like this, AC is constant, so cos omega ct, so that formula, so this is A, so this is A and then this one is B, this whole is B, so you can say this one is B, like this one is B and this one is A. So you can use this trigonometric formula again, cos A plus B is equals to cos A cos B minus sin A sin B. So you can use that formula here. So cos A, so this one is A and this one is, so this one is B. So cos A is omega ct, cos B is beta sin omega mt minus sin A and then sin B. So this one is B. So sin A is sin omega ct multiplied by sin beta sin omega mt. And the limiting case is that beta is much less than 1, like very small. If the beta is very small, then we can write cos beta sin omega mt approximately equals to 1 in this equation, and sin beta sin omega mt approximately equals to beta sin omega mt in this equation. So if we use this assumption in this equation, so it means that this part is equals to 1. So like this part, this whole part is equals to 1 and then this whole part is equals to this one, like AC cos omega ct minus AC beta sin omega ct and then sin omega mt. So we also know that this 2 sin A sin B. So we also know this formula 2 sin A sin B, like 2 sin A and sin B is equals to cos A plus B minus cos A minus B. Okay. So cos A minus B minus cos A minus B minus cos A plus B. So you use this formula, so the same as it is. So cos A, so over A is that one, so this is over A and this is over B. So A plus B and then A minus B. So upper sideband, lower sideband and the carrier. So that is the, you can see that the narrowband FM signal has the carrier and the upper sideband and the lower sideband. So you can consider few, you can note few points that the lower sideband and upper sideband, they are 180 degree out of phase because we have a negative sign in the equation. So that is why they are 180 degree out of phase with respect to each other. The second point you need to know that you are assuming beta, so that is modulation index is much less than 1. The other thing is that you can see that the narrowband FM signal has only 2 sideband, upper sideband and lower sideband, and the amplitude of the upper sideband and lower sideband is AC by 2 beta, and the deviation of frequency is limited, and the modulation index is k of f am divided by omega m. So that's all. I hope that you have understand the first form of the FM, which is narrowband FM, so which is the limiting case of the FM. So if you have any question, you can ask in the comment box, and we will try our best to answer your questions. Thank you for watching the video.